Swayam Prabha. Digital India. Educated India.
So the question that was asked is, why did we consider this migration from S3 to S3? Okay, so it is actually a simple concept here that when you are trying to, like, these atoms are moving, let us start thinking that the atoms are moving. So when it move from where to where it can go. So you can think of again, like you are sprinkling the atoms, what we thought it will fall everywhere, but slowly it will be going to the best place that it is possible, like water going into the valley or somewhere, right? Same here, it is like the S3 is the most stable site for you. So what we wanted to see is, like, when it is hopping, when this metal is hopping, we cannot just think of hopping alone, but one of the processes, like the metals are actually hopping, metal ions. If they are hopping, then they will be hopping from one side to the other side. What is the best possible site to hop again is obviously the most stable site. That's the reason you are trying to see from here to here, if it is happening, what will be it. When you are giving, like when you are discharging, it has to go through the solution to the cathode, right? So that's why, that's the reason we are trying to see this. Otherwise, like the ions, if they are static there, then we are not going to get the voltage in the, yeah, it matters, right? Like that's what we have shown you here. There are like 3 different paths when you considered. In one of the paths only, the migration energy barrier is very less. So obviously, the ion would be trying to go through this path than through this path. Like us, like when you are trying to cross a hill or something, you will be trying to see what is the easiest path for you to go from here to there, right? Like you will not be crossing uphill and go down unnecessarily. Yes, definitely affect. Yes, the mass of the ion will be affecting you in a different way, that is like through inertia, right? But what we are saying, as you said, it is absolutely correct. So once you have a potassium ion, it might be difficult for it to start moving it. But once it moves, then the barrier is actually very less. That's what we are saying. Okay, the inertia will be there, and that's what, like, the mass will be affecting it there. Okay. Okay. So till now, whatever we have seen is only for a single metal atom or single ion. That's what we have calculated, the single atom's adsorption energy, single atom when it is migrating, etc. So whereas when we are dealing here, what we are trying to start is with multiple layers. Like you know that, like in the real system, when you consider, there will be more than one atom that can be adsorbed, and they can be absorbing also more than one layer. Okay, always we think that, okay, one layer of graphite sheet is there, on top of which you are keeping one layer of lithium, but more than that also it can adsorb, and that's what we are going to study in this particular case.
What is the general electrolyte we keep there?
So in this case, we are not keeping anything, but like there are like propylene carbonate, ethylene carbonate, etc. So these will be like, I hope you, okay, anyway, I will write. So something like this. This kind of, obviously hydrogens and other things will be there accordingly. Okay. So that kind of thing, or there will be another CH3 group will be there. These are like commonly known, but there are others like glyme, diglyme, etc. So these are like ethers, CH3O, CH3 type.
There are any special reason we are keeping
a little louder?
Any special reason we are keeping this as electrolytes there?
No, so this is about the stability of the electrolyte. When you are considering the electrolyte, what it should be having is, when you transfer the electrons to this, like, so this electrolyte that is there, that is close to this electrode, can also be reduced or oxidized. Listen once. So when you have these electrons can go to this electrolyte and they can break them. What you want is something that is more stable, which will not be immediately reduced or immediately oxidized. So between these electrodes and the reduction and oxidation level, that should be maintained for this particular electrolyte. That's how generally you would be choosing. An electrolyte will be stable with the reduction and oxidation potentials of both the electrodes. That's what you will be choosing. So if higher the reduction stability, like if the electrolyte window is more, like HOMO-LUMO gap, you might have heard, no? Here, like the valence band, conduction band gap, if the HOMO-LUMO gap is very high, that's very good, that it is a very stable electrolyte. That's how you would be generally choosing. Now what we are dealing is, as I said, like multi-layer adsorption. Obviously this looks pretty small for you. Are you guys able to see what is there on the, yeah, okay, cool. So here, like what we are trying to study is layer by layer adsorption. You consider one, how many layers actually I can stack up of the lithium or the sodium, etc. So the ones that are shown in bold, for example here, are the maximum that we can load for each one of these systems, and that's what we are saying here. So you can see how we are doing this. This is how the reaction would be like for any particular layer that you are considering. The previous layer till you will be calculating what is its total energy and subtract the previous layer's energy and the total number of metal atoms you have added. So let us consider that you are on the second layer. Then what you would be doing, in order to add another layer of atoms, you first calculate the total energy of the system till the 2 layers and also the total energy of the system of containing the 3 layers, and you subtract how many number of atoms you have added for the third layer. That's all. So total minus the second layer minus how many number of atoms that you added for the third layer. That's all you will be doing. And so there are a few ways that you need to omit. Some of these possibilities you have to omit. I will be just telling each one of them. But please check here only one important point, that for the case of cobalt phosphide, you could load up to 5 layers. For cobalt, this is silicide, you can load up to 3 layers. Whereas if it comes to sodium, majority of them are only up to 3 layers. For potassium, only 1 layer. More than 1 layer, we were not able to load. How this would be affecting is what we will be seeing. So here we stop this multi-layer adsorption when one of these conditions are considered. First one, whenever we obtain a positive or near zero adsorption energy. So if adsorption energy is close to zero, what does that mean? The atoms are no more bound to the system. We don't want such kind of things, because we want the atom to go there and sit on the anode surface. That's what we want. So that's, for example, here all these positive energies, this one, all of these are positive energies. Whenever there is a positive energy, we will be immediately neglecting it. We will not be considering further. Additionally, in some cases, the average adsorption energy of Lth layer can be more negative than the L-1th layer. That means, if I am adding only 10 atoms, for 10 atoms, the adsorption energy is, for example, -3. If I am adding 20 atoms, I will never be expecting that it will go to -4. Why? Because when I am adding more and more atoms, the adsorption energy slowly decreases for the system. That's what we would be expecting, because it is already started. Metal and metal atoms will be there. They will be repelling with each other, right? There is no attraction between the non-metal and the metal atom. So whenever we obtain anything different than that, we will stop it there. What is the reason? We think that that is leading to the agglomeration. That means the atoms will start to bind with each other. That's the reason the total energy is increasing. So we will not be considering that. Third case, the adsorption energy did not change much as we move from L-1th layer to Lth layer. If it is not changing, that is also not something that is expected. So we will not be considering. So for the earlier case, 5 and 3 layers of lithium adsorption on cobalt phosphorus, if you see, so here it was 0.015, but it started to increase once you go from 5 layers to 6 layers. So that's why we stopped at the 5 layer itself. Similarly, for other things also, here you see 0.04 to 0.027 it is going. That means this is higher. Oh no, sorry, not this one. This is like correct only. Where is the other one? So here if you see, yeah. So sodium case 0.016 and 0.115. So like suddenly it is increasing, like 0.016 to 16 versus 115. That is very high. That automatically suggests that there is some agglomeration that is happening. That's why we don't want to consider that. So this is the, so as a whole, like we have seen how many number of layers we can adsorb, and what it corresponds to, it's something that we will be seeing. So this is essentially the metal insertion voltage calculation. As I said earlier, if the voltage, so why we are considering the anode voltage is equals to metal insertion voltage? Because when you are supplying, when you are doing this charging process, you are essentially taking the metal ions and you are inserting it into the anode surface. That's why it is also called as the metal insertion voltage. And you can see this particular reaction here as a whole. What is this? Metal plus whatever the antimexene is there, that is forming this total compound. And this is nothing but your individual half cell reactions. That is, as a whole, is coming as the adsorption energy only. That's the reason we are calculating the adsorption energy and we are using it for the potential calculation. If the difference between the, so this is nothing but your reduction potential, right? You have an antimexene, and if you are adding an electron to it, what is reduction potential? Once you add an electron, how much amount of energy will be released is nothing but your reduction potential. So here you consider CO2x2 and CO2x2 minus. Similarly, for this case it is M plus and M. If you have a metal atom and if you add the electron, how much it is. If it is close to 0, what does that suggest? This particular anode material is as good as the original anode. That is, like, for example, if you consider lithium ion battery, what is the best anode that you can get? Lithium itself, because for it, if you consider the lithium metal, if you add one more atom or if you remove one more atom, it should not be happening anything. So if this particular case also, if V is equals to 0, then that suggests that it is as good as the electrode material itself by itself. So that's what we will be seeing, and that's why we need to have a close to 0. So the above reaction is essentially nothing but the adsorption of the metal atom onto the surface, and in general you might have heard this value delta G, Gibbs free energy. Have you heard Gibbs free energy or no? Majority no? Yes, yes, okay. So how do you calculate the Gibbs free energy? Gibbs free energy is nothing but G is equals to H minus Ts is the way that you would be writing, and H is nothing but U plus PV. So if you rewrite that U is nothing but your internal energy of the system, and that internal energy here is nothing but the adsorption energy according to the reaction. And then what you have is P delta V term and T delta S term. Here we are neglecting both the P delta V and T delta S, because the P delta V here, delta V corresponds to the volume change, and you are considering a anode material for which the changes will be very minimal. Even if you are assuming that, okay, you are adding the metal atom change will be only minimal, so that if you are assuming, for example, 100 angstrom cube, 5 layers I have added, that means roughly I can go in this direction 10 angstroms, in this direction another 10 angstroms. So that corresponds to only 100 angstrom cube, and at the ambient pressure, which is nothing but your 1 bar is equals to how many pascals? 10 to the power of 5. So if you consider that way, the 1 electron volt per angstrom, this 10 to the power of 5 pascals essentially corresponds to roughly 10 to the power of minus 6, right? So if you multiply that one with the 100, essentially you will be getting in the order of 10 to the power of minus 5 electron volts. That is very, very small number when compared to the adsorption energies. What is the adsorption energy ranges that we have seen? Minus 1.3, 1.8, 2 also, minus 2 also we have seen. That is in electron volts. This is in 10 to the power of minus 5 electron volts. Okay. So close to micro. So that's the reason we are neglecting the P delta V, and also similarly the entropy changes will be very minimal, because this is a solid material. As you might have learned regarding the entropy changes will be maximum for the gases, not for the solids or the liquids. Since this is a solid, you can safely assume that this is not going to affect, that's all. So as a whole, delta G, the calculation of the voltage is essentially again calculating the adsorption energy, and you are going to use this equation where delta G is equals to minus NEF is what we know, right? Where E is nothing but the electrode potential, that electrode potential is nothing but the voltage here, and that voltage is nothing but the adsorption energy. So accordingly the voltage is coming as delta E by F. So you calculate the voltages for each of these systems along, like for this lithium, sodium and potassium, and you can see here that voltage is crossing 0 for certain cases. Whenever the voltage is crossing 0 means that corresponds to a negative. Voltage is negative means if you go back to this particular equation, delta G will become positive. When delta G is positive, is that a spontaneous reaction or a non-spontaneous? Non-spontaneous. So you will not be considering that kind of reactions. So whatever is there above 0, only the positive values of the voltage are the ones that I would be considering as proper. And you can see here the number of lithium atoms per formula unit I can add. So if I am considering COX is here cobalt, whatever anti-mixing non-metal atom I am considering. So here I can go up to 5 for the case of phosphorus, whereas for other ones you can see for the sodium it is going up to 4 is the maximum, whereas for the case of potassium I cannot go even for 2. So although potassium has a good migration energy barrier, I mean low energy migration energy barrier, because of its strong adsorption energy, it couldn't load more number of atoms. What is the problem for this? The average voltage will be very high if this is considered. So if you consider the average voltage values, I don't think I have given here, but you can roughly see this. So average means like you need to consider all of these points, and you need to average that over. Okay, that's all. So if you see, then for the case of sodium and lithium, it will come around some 0.4 to 0.5, whereas this one, if you consider, this will be above 0.6 because this is the minimum and this is the 1.2 is the maximum. So we wanted what? The average voltage should be as low as possible. Why? Because your cell voltage will be high only when the anode voltage will be less. So here, if you are using potassium, the anode voltage is very high. So we are not supposed to consider this materials as anodes for the potassium ion batteries. That's what it suggests. So these are the voltage corresponds to Li4, COSI, and these are the ones. These are reaching close to 0. So that's the reason we are stopping. But you can see that you can absorb up to 4 layers or 5 layers on silicon and phosphorus. So for the lithium cases, when you are considering, these two anode materials can become very good materials. Okay, that's what it suggests. Similarly, for the case of sodium, majority of them are going to 4, so that is all of them are good only. For the potassium, only K2COX is the only thing that is available. Yeah. Next, we calculated the specific charge capacity. I told you about the specific charge capacity earlier. So we already calculated the voltage. Now what we wanted to calculate, how much amount of the charge this material can hold. Okay. Potential is only telling about how much it can deliver, right? How much amount of work it can do is what it will be suggesting. Whereas the charge is about how much amount of the charge this particular material can hold is telling, will be understood by calculating the specific charge capacity. So you can clearly see that for the case of lithium, you can see more than 1000. So the batteries that we are using generally will have about the specific capacity of 300 milliampere hour per gram. What we found is that this particular material can have the specific charge capacity. I am saying only about the anode, but the 300 is reported for the overall cell. Okay. So here what I am considering is only for the anode, but this anode material has more than 1000 milliampere hour per gram. So which is a very good news for us that these materials can be having a good potential to use in the lithium ion batteries. Similarly, for the sodium, if you see, majority of them fall in the range of 400 to 600 milliampere hour per gram, which is also very good. So we can understand, for example, how these values are changing by easily knowing this specific simple equation itself. So what is the equation? You are calculating the number of moles and the charge and the Faraday constant divided by the molecular weight of the complex that you have formed. So you know that Faraday is like charge per mole and weight is gram per mole. Both of them will cancel and give you charge per gram. Okay, that's what we wanted. That is what is the specific capacity of what we are saying. And for this case, as you can clearly see, if the molecular weight is increasing, obviously the capacity will be decreasing, right? Because it is in the denominator. And you can see that whenever you are considering a specific material, for a specific material and the same number of atoms when they are adsorbed, the one that is having the highest weight will be actually having the lowest specific capacity. And if you see, for example, here, so if you see here, there are like 3-4 materials are there that are giving. So green color one is phosphorus, okay, and red color one is sulfur and selenium. So let us consider phosphorus and selenium. Which one is having the higher weight, phosphorus or the selenium? Selenium will have the higher weight. Since both of them are absorbing, let us consider the sodium, particularly on sodium, both of them are able to absorb 3 layers. That's what it is suggesting. 3 layers of sodium atoms are there on both selenide as well as the phosphide. But since selenide will have a higher weight, what we would expect? It should have a lower specific capacity. So let us see here for the case of selenide, and this is the phosphide and this is the sodium. This is sodium here and this is the selenium here. So selenide should have a lower specific capacity, and that's what you are able to see. So similarly, once you identify a material, like for example cobalt selenide only if you considered, and if you know how many number of atoms that are absorbing, then you can even calculate whether the potassium will be the one which will be least or the other ones, simply based on the number of atoms that are absorbing and what is the molecular weight. So what we are doing here from first principles is to obtain the adsorption energy there, and that is what is helping us to identify how many number of atoms we can actually absorb. All other things are constants only. So as such, we find that there are a few materials that can absorb, that can have very high specific capacities for lithium. Majority of them are very good, have very good specific capacities for the case of sodium. So that's the important point that we learned. So those materials that have less voltage and also high specific capacity are the best materials that we can use for as the anode materials in the batteries. So we finally, there are a few more things that we also consider. For example, after loading for 5 layers or so, we need to check whether thermally they are stable or not. That means like I have loaded 5 layers, and if I start using them, they can form an agglomerate again, like they can form a cluster. Although my adsorption energy is saying it is not, I need to really consider the temperature and see. So for these ones, we have considered like around 300 Kelvin, and we have, that is your room temperature, and we ran these systems for about 15 picoseconds. This is very less time on the human scale, but when you are doing the molecular dynamics simulations, these are very high time scales. So, and we find that there is nothing that is hugely changing, and there is no formation of agglomerate in these systems, which suggests that these materials are pretty stable. Same thing we also did for the sodium case, and we also see that the energy changes are minimal. So, if there is any formation of any new compounds, what will happen? Energy will be changed as a whole a lot, right? Like if there is a new bond is formed or a new bond is broken, so energy changes will be observed. But here you are seeing that the energy changes are only pretty minimal. So these energy changes are pretty minimal here, suggesting you that there is no problem for loading up to even the 4 layers. That's what we are learning here. So we wanted to understand why this stability is more for the case of sodium and lithium, but not for the potassium. This is one thing. So we said that we can load up to 5 layers in the case of lithium on these materials, and we can load up to 4 layers for the sodium, but only 1 layer of potassium was only done. So in order to understand that, we have plotted, these are similar to the plots that I have shown you in the beginning. These are called as electron localization function plots. Here there is a color coding is also done, where a red color corresponds to, there is a strong electron density between them, and if this is like a green color, that is close to what is called as like electron gas type. Okay, so these are free electrons are there, and if this is in the blue color, this suggests that electron density is not at all there. That is okay. So these are the things that if you are considering, you can clearly see that when you start at the beginning, the first layer, when you are considering, there is only ionic type interaction, but afterwards there is like a free electron gas type interactions are there between the atoms, that is helping it to load more number of atoms on the cases of, for the lithium and the sodium cases. Whereas if you see the same things in the potassium, you see that there is a huge blue color between the atoms. That means these atoms are directly seeing each other. There is nothing that is filtering or screening them. So that's why they will not be that much stable. That's the reason when you are going from first layer to second layer, we are not able to load more number of atoms on these systems. We have also finally considered how much the adsorption, and with the adsorption of these materials, how much there will be a increase in the interlayer distance. This is to know whether your batteries will be bulging out or not at the end. Okay, so when we are seeing this, we saw that the amount of change for a single layer of lithium atoms or something is pretty little. Even for the case of sodiums, it is very little, suggesting that the low interlayer separation is useful for the stable cycle life of this battery. So as a whole, these are the points that we learned through today. So first one is like the newly developed cobalt antiamazines are electrically conductors and dynamically stable. So they are very good conductors, so we can use them. Similarly, we have considered a high chemisorption we observed. That means they will not form any dendrites on the system. Next one is low diffusion energy barrier is observed for all of them. Since there is a low diffusion energy barrier, that means fast charge discharge rates will be there. Specifically, high specific capacities are observed for the case of lithium as well as for the sodium case, suggesting that they can be very much useful. And finally, we have seen that maximally lithiated and sodiated systems have high thermal and electronic stability, and negligible expansion is there. So considering all the factors, what we find is COP, that cobalt phosphide, is a promising anode material for all 3 types of batteries, while silicide is promising for lithium and sodium. All these others are reasonably good. They are not extremely good, but they are reasonably good for the case of other ones. So this work is done specifically by Subhadeep, his PhD student working in our group. He did majority of this work, and these are the funding agencies. IIT Madras has supported us through the startup grant as well as the SERB. That's all. So how much we have an additional 15 minutes. So I will try to show you another concept if you don't have any other questions. If you have questions, I will take them. So this is a slightly different concept. This is here we are trying to show the degradation of the pollutant molecules. Okay, these pollutant molecules are called as perfluoroalkyl substances, and how do we degrade these substances is what I am going to show you. Okay, so you all know about hydrocarbons, right? So what are hydrocarbons? The systems that contains carbon and hydrogen bonds, like on the left hand side. So if you wanted to understand what are perfluoro, so you replace every hydrogen atom with fluorine bond. That's what is called as the perfluoroalkane systems. Okay, so what is the difference between these two? Only the fluorines, that's all. Hydrogens are replaced with the fluorines. What is the use of these systems? Here you do know that carbon forms its strongest bond with the fluorine atom, and that's the reason these compounds are very much useful. Okay, so if you see just the carbon fluorine bond energy, you can see that it is about 130 kilocalorie per mole. If you know, what do you know what is the room temperature energy corresponds to roughly? It is just 0.6 kilocalorie per mole. If you are calculating it in terms of electron volts, it is simply 25 milli electron volt. Whereas this bond strength is about 130 kilocalorie per mole, that is roughly like 200 times more than the room temperature. 200 times more than the room temperature. And if you see the other bonds, so this is like CH bond is 98, CC bond is 83. So when the CF bond is formed, that itself is like one of the strongest bonds. That means you cannot easily dissociate them. And industry has actually used this one for its these PFAS compounds to prepare various kinds of industrially useful things. I will show you all of them soon. And among these perfluoroalkyl substances, PFOA and PFOS are the most commonly available one. What is PFOA? Perfluorooctanoic acid. PerfluoroOS is sulfonic acid. Okay, these are the two compounds that are widely available, okay, widely used in the industries. So if you replace all the hydrogens, that is called as a perfluoroalkyl substance. If you replace only certain ones, that is called polyfluoroalkyl substance. So that's the reason this PFAS as such are called as per and polyfluoroalkyl substances. These are the various kinds of applications that you can see for the PFAS substances, and most of them you might be using already. Okay, so when you are using a non-stick cookware in your house, it's essentially is having the PFAS, and the recent ones that you are seeing, they will be writing that there will be no PFOA, no PFOS on that. Please check when you are buying these kind of pans, because these materials PFOA, PFOS, which were considered as very useful, are very harmful to the human and the environment. Okay, that's the reason we are trying to degrade these materials. Okay, so whenever you are buying a new non-stick cookware, you should tell your parents, or when you are buying, you should go and see whether that is free from PFOA and PFOS. And they have other wide variety of applications, from photography, firefighting foams. If you go and see this firefighting foams, here it is just CO2 that you would be using. But if you go to army bases, camp bases, if you see, they will be using this PFAS. Because of this CF bond is very strong. When you just use it, the fire cannot burn that one. Okay, if you use alcohol or something, it can easily break the bonds and it can combust. Whereas if you use the CF containing these PFASs or something, it cannot break those bonds. The fire cannot break those bonds. So these materials will be stopping the fires. That's the reason they are being used in the firefighting foams. But due to using a severe usage of this firefighting foams, like military people will be getting training of how to stop the fire, etc. So if you see in the USA, at least this is the place where we have studied. When I studied in the USA, this particular project, they have a lot of these military camps, and all these bases were severely polluted with this PFAS materials, okay, because of their high usage. Like this, there are various other applications, paints, shampoos, etc. So you don't want your paint to be removed immediately. You don't want that to be affected, right? Whether you put water or oil, nothing should be touching that. But essentially what you are bringing is these dangerous chemicals inside your house. That's what you are essentially doing. It is a harmful chemical. Exactly, that they do not know earlier, right? This is how general science will go on. Like it will be a cycle always. Like you will be considering that something will be useful and you start, and then you will find that it will have a malicious effect, and then slowly you try to degrade that one and remove that using, like DDT powder. We use it to put everywhere. Now this is considered as a carcinogenic. It has its application, like as I have shown here, it has its application, but it also has a deleterious effect. That's what we will be learning, only the deleterious effects slowly, like our mobile phones, right? they have some positive things, but also it has a big effect of taking away our focus, our attention, right? We are already lost and we cannot go back. Certain things are like this. So technology will always have that, science and technology both will have the positives and negatives. So that's what we learned. So these are certain places in the USA where they found like all these marks wherever are there. The permissible amount of this perfluorooctanoic acid or sulfonic acid is about less than 70 ppt. This value is actually decreasing further. I mean, they are finding that even if you have 30 nanogram per liter, 30 nanogram per liter also can be harmful. That's what they are finding. So this was slightly older, around 2020 it was about 70 or so, and you can see that majority of these places where you are seeing this yellow or brown color, they already have a lot of that kind of pollutants in the drinking water resources, and this is even coming to the new babies through the breast milk fed by the mothers. That much it has already penetrated into the system, okay? And in India also, in Tamil Nadu, there are various places they show this particular curves, and you can clearly see, I don't know the exact names of these districts, etc. Tirupur or something like that, it is there, but at least I can tell that in Tamil Nadu it is there, where there are bases. You can find that already our water is also polluted. That's all the major point that I want to tell. So apart from the uses, the CF bond strength is also harmful. Why it is harmful? Because this is a man-made chemical. So the biological organisms are not evolved to break this particular bond. So what happens once this PFAS, PFOA are consumed, they will start accumulating in the body. Certain cases they will be should be thrown out. However, send out through our urine or something. But in this particular case, they started to accumulate, and you can see in the human body they are accumulated at lungs, brain, bones, etc., to certain extent. So once they start accumulating, they will start hindering the normal mechanisms. That's how they will make harmful. And these are also known as persistent chemicals, for the reason saying that they will be continuously there. They cannot be degraded because our organisms are not evolved to degrade them, and you do not have any other methods to degrade them as well. Okay, I hope that. So the recent experiments have shown that if you use the reduction methods, they can be degraded. Obviously, these are not the methods that we are trying to use inside our human body, but once the general procedure is you will try to extract this, I mean using filtration methods type, you will be extracting these kind of PFAS chemicals through the normal filters also doesn't work, but there are certain additional filters that you would be using to filter these chemicals, and after filtering whatever the residual part will be there, that needs to be treated. The treatment process is what we are trying to study, like what kind of things we can use to treat this chemical. So recent experiments suggested that this is based on the cobalamine complex. So cobalt containing catalysts can be useful to degrade the CF bonds is what they studied. Another study also showed if you use this hydrated electrons, these are powerful reducing agents, they can also be used to degrade the compound. This is what they have studied. So what we thought of, can we use simply by adding the electrons to the system? How do you do that? You can use a metal, and then you can use sunlight or a UV light in order to generate the electrons, and these electrons can be solvated. That's what we call as hydrated, and whether these hydrated electrons can degrade the compounds or not is our interest. And what we are doing the simulation to study these things. So I'll skip these ones because of the time lag. So what we essentially found is this is our neutral system. So this is the PFOA molecule. Whatever you are seeing as small lines, those are the water molecules there. So we have solvated these molecules and we tried to study whether they will be degrading or not. So once we added one electron to the system, as you could clearly see, the bond is dissociated. When you added more electrons, more number of bonds start to degrade. So this clearly suggests that if the reduction method is useful in order to degrade these compounds. And the number of CF bonds dissociated are directly proportional to the number of electrons added into the system. We have studied like about 16 simulations, although I have shown you only 6 of them here. We have considered 16 simulations, and in all of those cases, we observed that if you add the electrons, the bonds will be degraded. So which is one of the important points. Additionally, we have also studied by adding positive charges to the system, and we observed that oxidation is not going to helpful. Only reduction is the one that is helping these bonds to degrade. Additionally, we have found that this degradation process is occurring in an ultra fast manner, which is very much important. If you are trying to degrade these substances for like 10, 15, 20 days, that is useless. Here what we are seeing is it can be degraded in few femtoseconds itself, it can be completely degraded. And we shown here the bond length changes. As you can clearly see, when it is standing it is about 1.3 angstrom. So you do know the normal CC bond distance. Single bond CC bond distance is how much? Single bond CC bond distance 1.54. Okay, 1.3 is about your double bond distance, and lesser than that will be the other ones. So here 1.3 is for the CF bond distance, equilibrium bond distance roughly. Okay, so this is the equilibrium bond distance, and as you can clearly see, these ones are going to 2.5. That suggests that it is bond is dissociated. That's all essentially this suggests to you. Okay, so for -1 charge this is how, and -2 charge you are seeing clearly that the bonds are dissociated. And additionally we have also seen how this bond is actually dissociated. For this, what I have studied what are known as the spin densities. So we all know already, I believe, that electron can behave as a particle as well as a wave. Wonderful. So here you are seeing the distribution of that one additional electron all over the place. Okay, so in the beginning of the system, beginning of the simulation, the electron is spread over all the molecule, but at a later stage it is getting localized in this particular case, and then there will be a dissociation of the bond. So that bond dissociation is what you are seeing after the localization of the electron. So these are what are actually called as spin densities. So these are called as spin densities, where the charge is associated with the fluorine atom, whereas the spin part is only localized on the carbon atoms, and that's what we have seen. So like this, we have performed 12 different kinds of simulations. When you are having these 2 electrons, the fluorine atoms can go in the cis manner or a trans manner. You know about cis trans, right? So 2 fluorines can go in from the same direction, etc. We have studied all of those things. Essentially, we found that for only cis type elimination, spins were localized on the carbon atoms. You can see here, these are the spins which are opposite. So as a whole, the system is always non-magnetic. One case it is like anti-ferromagnetic, another one is non-magnetic. Have you heard of these words, anti-ferromagnetic and non-magnetic? So here one spin is up, another spin is down, but exactly their magnitude are same. So this cis type case, it is exactly anti-ferromagnetic type. Whereas in the trans elimination, we find the system to be completely non-magnetic. There is no spin is there. Okay, these are just some important points. And what we additionally observed was there is a formation of the C double bond C after the elimination of these fluorine atoms, and that is helping further to degrade these systems. Okay, so essentially apart from all of these ones, we also observed the formation of this hydrogen fluoride, which is one of the products that was also observed in the experiments. Even the C double bond C was also observed in the experiments, suggesting that these simulations are predicting something good. So there are other kinds of, we are also studying this hydrated electron assisted degradation. So he's as I told earlier, Brian is the one whom I worked with. So this work is also done along with Ravindra. So, and these are the acknowledgements. So conclusion is, this is the first study where we have shown the real-time degradation of the perfluoroalkyl substances using the electrons, and these excess electrons are enabled the dissociation of the CF bonds, and dissociation occurred in the ultra fast scale, and we were able to see the C double bond C formation. This particular article was on the front cover of that PCCP journal, and it was highlighted by our Department of Energy of USA and also various other places. So if you are just interested in seeing the article, not just the complete article but the news articles, you will find several of these news articles on this, like on Medium and various other places you can see. That's all. You have any questions, I will be happy to take.